This is Recitation 9, and today we will talk about Ampere's law and Biot-Savart law. If we have a wire with current I, this wire will create a magnetic field. How to calculate the magnetic field created by a wire with current I? We will have two laws that will tell us how to do that. We will start with the fundamental law, Ampere's law, that tells us B magnetic field dot product dr around closed loop is equal to constant that we will call mu naught times current enclosed by this loop. So this is the law, and now we will apply this law to the situation when we have a current, a wire with current I, and this will be infinitely long wire. We will find the magnetic field created by this infinitely long wire. Let me make this wire a cylinder, and this cylinder has radius r, big R. And I tell you that current I is uniformly spread over the cross section of this wire. What is magnetic field? Everywhere at r, arbitrary r less than radius of the wire, and at arbitrary r that is greater than r, which means outside of this wire. Before we even start calculating the magnetic field, let's discuss the direction of the lines of the magnetic field. The lines of the magnetic field created by this wire with current I will be circles. I will draw this circle, and this part of the circle is in front of this wire, so let's make this clear that this is in front of this wire. I will make it a little bit better for you to understand what's going on. So now you can see that part, and you cannot see it here. Okay, now what is the direction of the lines of the magnetic field? To find the direction of the lines of the magnetic field, you need to use right-hand rule. Ironically, I use my left hand because you see my mirrored image. So what you need to do, let me put this two so far back. This is my wire with direction of current I is this direction. Now I put my thumb along the current, then I bend my fingers, I grab the wire, and look, here above the wire, my fingers come out of the board. So here the direction of the magnetic field is out. And then here below the wire, my fingers bend go into the board. So direction of the magnetic field at this point is into the board, which means that the direction of the lines of the magnetic field are in, let me see, is it clockwise or counterclockwise? Depends which way you look. So it will be down at this side of the circle that is in front of the wire. So in green, we showed the direction of the lines of the magnetic field. So the lines of the magnetic field created by this wire are these circles with the direction that we indicated. Now we need to find the magnitude of the magnetic field. First of all, we will consider this region with r greater than the radius of the wire. So if I draw the side view of this wire, and let's look at this side at this wire. So current is coming out, and those are the lines of the magnetic field. We put them in pink, so let's keep this pink. Lines of the magnetic field will be circles, and if current is coming out, what will be the direction? To find the direction, again, I put my thumb along the current with my right hand, and then you have to do it with your right hand. And then I bend my fingers, I grab the wire, and here my fingers go up. So this is the direction of the lines of the magnetic field. Okay, now I look at the Ampere's law. We find the magnitude. What will be dot product B dot dr? B dot dr is simply a product because lines of the magnetic field are parallel to infinitesimal small steps that we follow when we go around the loop. So this integral, this dot product is simply product B times dr. Magnetic field is the same at each point of this loop from symmetry. We can take B out of this integral. Integral dr is circumference. This is my arbitrary r. So I put B, and the circumference is 2 pi r. And this is equal to mu naught current enclosed. What is enclosed? Everything. Current I. It is equal to mu naught I. So the magnetic field at r greater than radius of the wire is mu naught I divided by 2 pi r. And the direction is counterclockwise. Now we will work at r that is less than the radius of the wire. So I consider the same wire. This is the side view of the wire. Current is coming out. So the lines of the magnetic field inside and outside of this wire will be circles. The direction will be the same. We already found it using the right-hand rule. Now we are within the cross-sectional area of this wire. We are right here. Our little r, I will use different color. Let's use blue. This is our little r, arbitrary. And now I need to work with the left-hand side of Ampere's law. Integral B dot dr is no changes here. Again, the same logic. B is parallel to dr at each point of this loop. We can take B out of integral because of symmetry. Integral dr is just circumference. Radius is little r. So I put B times 2 pi r. And this is equal to mu naught current enclosed. What is current enclosed by our arbitrary loop? What is current enclosed right here? Well, let's recall what is current density. So what is current density? We talked about it. By definition, current is integral J dot ds. This current, it was given that it is uniformly spread. So I can take J out of this integral. It is J times area. Let's call area A. And then J is I over A. So what is J for this problem? J is current I. Since it is uniformly spread, J is constant. It is current I divided by cross-sectional area. What is cross-sectional area? Radius is capital R. So cross-sectional area is pi r squared. What is current enclosed? It is enclosed by this arbitrary pink circumference. It is current density I divided by pi r squared times area enclosed by this pink circumference. What is area enclosed by this circumference, by this circle? What is area enclosed by this circle? It is pi little r squared. All we need to do is just simplify this expression and solve for B. What this means that current enclosed by this loop, and I remind you that this loop has arbitrary radius r, is J, which is I over pi r squared, capital R squared, current density, times area enclosed by the circumference of arbitrary radius r, which is pi r squared. All we need to do now, we need to solve for the magnetic field B. What will be the magnetic field B? Let's look at this. R and r squared cancel out. Pi and pi. Now we have B, magnetic field, which is mu naught I divided by 2 pi r, capital R squared, and little r here. This magnetic field is a vector, so we do not forget to indicate the direction. What is the direction of the lines of the magnetic field? It is counterclockwise. All we need to do now, let's plot the picture of the lines of the magnetic field inside and outside of this wire. Can I erase real quick? All we need to do now, we need to plot the magnitude of the magnetic field inside and outside the wire. Magnitude of magnetic field as function of the distance from the center of the wire. I'll just go to the right of this wire. So this is the radius of the wire, and inside my wire the magnetic field is proportional to R. I draw a line that is proportional to R. This is proportional to R, and outside of this wire, for R greater than radius of the wire, I have dependence 1 over R. 1 over R. At the boundary, at R equal to the radius, magnetic field is mu naught I. Is it a straight line? Let me make it a little bit better. So right here at R equal to little r equal to radius of the wire, the magnetic field is mu naught current I divided by 2 pi capital R radius of the wire, and of course both solutions give me the same result. If I put capital R here, R and R is cancelled, and at the boundary I get the same result from both formulas.